Alright guys, we're going to finish up 5E, and we've been talking about correlation, and just to briefly review, we had looked at these two different graphs, or these two different scatter plots, in which on the horizontal axis we had a forecast temperature, and on the vertical axis we had the actual temperature, but this is a same day forecast. And then over here on the horizontal axis we had a 3-day forecast, and then on the vertical axis the actual temperature that day ended up recording. And so we had said that because the 3-day forecast is there's more uncertainty, this scatter plot was much looser, or more specifically the correlation was not as strong as the scatter plot that corresponds to the same day forecast. Okay. Alright, so now what we're going to look at are some possible explanations for correlation. So we've seen the different types of correlation, be it positive, negative, okay, or no correlation. If there is correlation, why is the question. So the first thing is it could just be a coincidence. Now I would say this is probably rare, especially if the correlation is rather strong. Now if it's a very weak correlation, then it could very well be due to just coincidence. Secondly, both variables might be directly influenced by some common underlying cause. So if you think back to that in 5B where we discuss confounding variables, a variable in a statistical study that's not accounted for, but that could be responsible for the actual results in a study, that's the same thing going on here. So maybe there is some underlying cause that we don't know about yet. Okay. And then number 3, one of the correlated variables could actually be causing the correlation. Okay. But notice it says, note that even in this case it may be only one of several causes. Okay. This number 3 is one that we have to be careful with, because as humans, guys, we could start debating as to the reason why we think this way, but typically when we see that two things are related, or that there's a correlation or correspondence or association between two things. I know in class earlier today I lectured, we saw how drinking coffee could we saw this in this class, the consumption of coffee could be correlated to the incidence of lung cancer. Okay, and when we see that correlation, we automatically want to think that one is causing the other. But lots of times, and I would even dare to say most of the time, that's not actually the case. That there's actually another variable or some other underlying cause that's responsible for that correlation. Okay, so proving that one variable is actually causing the correlation can actually be rather difficult. All right, but anyway. All right, so here's an example. Consider the negative correlation between infant mortality and life expectancy. Which of the 3 possible explanations for correlation applies? Well, we saw this in a previous video. Okay, so on the horizontal axis we have life expectancy, and on the vertical axis we have the incidence of infant mortality. Now this is numbers of deaths per 1,000 births. Okay, and so what we noticed was that there's a negative correlation here, because the data seems to be going downhill, and as life expectancy increases, we tend to see a decrease in infant mortality. Okay? But it's not that the increase in life expectancy is causing the decrease in infant mortality. It's an underlying cause. It's that countries that have these higher life expectancies, they also have access to better health care. Okay, or better nutrition. Okay, they're better able to take care of themselves and thus ensure that their babies are born alive. Okay, so that would be an example in which there's an underlying cause that can explain that correlation. Okay. All right, now there's a video in Blackboard that you can watch for this, because I can't play it here for you to be able to see it, but I'll briefly discuss it. So in the video, it states that, it's a very interesting video, by the way, guys. You should watch it because she gives some other examples of correlations, so some that are really quite surprising. But anyway, there's a correlation between ice cream consumption and drowning. So in other words, that's a positive correlation. As the amount of ice cream consumption increases, so too does the incidence of drowning. Now, intuitively, we know that the ice cream is not causing the drowning. Okay? There's an underlying cause, and that cause is that when do people typically increase their consumption of ice cream? During warm weather. And that also is when people tend to go and be in these bodies of water. And unfortunately some, because higher numbers of people are swimming and doing things in water, there are going to be more drownings. Okay? So there is a correlation between those two variables, but one is not causing the other. There's an underlying cause. Okay. All right. Okay, so what are some guidelines for establishing causality? So let's say you've determined, let's say you've gathered data and you've made a scatter plot, and you can see that these two variables are correlated. Now, it could be either positive or negative, and it can be, let's say it's a strong correlation. Okay, so how can we figure out, is one variable actually causing the change in the other? Well, let's look at these. It says, look for situations in which the effect is correlated with the suspected cause, even while other factors vary. Okay, so let's say the conditions vary, and you're still noticing this same correlation. Number two, among groups that differ only in the presence or absence of the suspected cause, check that the effect is similarly present or absent. Number three, look for evidence that large amounts of the suspected cause produce larger amounts of the effect. Number four, if the effect might be produced by other potential causes besides the suspected cause, make sure that the effect still remains after accounting for these other potential causes. Number five, if possible, test the suspected cause with an experiment. Okay. And this can be done, okay? Sometimes this is difficult to do, though. If the experiment cannot be performed with humans for ethical reasons, consider doing the experiment with animals, cell cultures, or computer models, okay? And this is typically done. And we're going to see an example here in a minute. And then lastly, try to determine the physical mechanism by which the suspected cause produces the effect. Okay, so you've got this list of 6 things to try to establish causality. That's why I was telling you earlier that to prove that one variable is causing that correlation can be rather difficult. So here's an example. Okay, so it's a case study: airbags in children. So by the mid-1990s, passenger side airbags had become commonplace in cars, and statistical studies showed that the airbags saved many lives in moderate to high-speed collisions. But a disturbing pattern also appeared. In at least some of the cases, young children, especially infants and toddlers in child car seats, were killed by airbags in low-speed collisions. Okay, so what we have going on here is we've noticed a pattern or a correlation. Okay, It says, at first, many safety advocates found it difficult to believe that the airbags could be the cause of the deaths. So we're seeing an increase in the usage of these airbags, or these airbags being deployed, and also a corresponding increase in infant deaths. It says, but the observational evidence became stronger, meeting the first 4 guidelines for establishing causality. For example, the greater risk to infants in child car seats fit Guideline 3. And Guideline 3 was look for evidence that larger amounts of the suspected cause produce larger amounts of the effects. So with increased airbag deployment, we saw an increase in infant death. Let's see. Because it indicated that being closer to the airbags increased the risk of death. A child car seat sits on top of the built-in seat, thereby putting a child closer to the airbags than the child would otherwise be. Okay. So when these airbags open, guys, they open. There's actually an explosive that is triggered, almost like the shell in a gun. Okay, and these airbags can explode rather forcefully. And it says to seal the case for establishing causality here, safety experts undertook experiments using crash dummies. They found that children, because of their small size, often sit where they could be easily hurt by the explosive opening of the airbag. The experiments also showed that an airbag could impact a child car seat hard enough to cause death. Thereby, they were able to reveal the physical mechanism by which these deaths were occurring. And if you look up here, number 6 was trying to determine what mechanism is actually causing the suspected correlation. Okay. So there was a lot of work and money put into this. I can remember, seeing commercials on television of these crashes, or on the news, different things. All right. Okay, so what about confidence in causality? So possible cause. Okay, so one variable could possibly be causing another. It says we have discovered a correlation, but we cannot yet determine whether the correlation implies causality. And this happens in the legal system. In the legal system, possible cause, such as thinking that a particular suspect possibly caused a particular crime, is often the reason for starting an investigation. And then we have something a little stronger, probable cause. We have good reason to suspect that the correlation involves cause, perhaps because of some of the guidelines for establishing causality are satisfied. And then in the legal system, probable cause is the general standard for getting a judge to grant a warrant or search. Okay. And then finally, cause beyond reasonable doubt. I love kind of the legal parallels here. I think that helps make this more understandable. Cause beyond reasonable doubt. We have found a physical model, so think about the crash test dummies, okay? We have found a physical model that is so successful in explaining how one thing causes another that it seems unreasonable to doubt the causality. Okay, so we go ahead and assume that one is causing the correlation in the other variable. Now, in the legal system, cause beyond reasonable doubt is the usual standard for convicting somebody. It generally demands that the prosecution show how and why, essentially the physical model, that the suspect committed the crime. Now, note that beyond reasonable doubt does not mean beyond all doubt. Okay? That's why, in the legal system, it's possible to convict an innocent person. But that's why in the legal system, guys, although People don't naturally assume this, but in the legal system, you are presumed to be innocent until proven guilty. But unfortunately, because of the way our minds operate, when somebody is charged with a crime, or even when they're being investigated, we automatically assume that they're guilty. Okay? And that can be very problematic. That's why jury selection is so crucial, you know. All right, so let's look at a couple examples here. These are some good ones, guys. I enjoy these. Okay, so number one, it says determine whether the variables in the following would be correlated. If they are correlated, is the correlation positive or negative? This is an interesting one, I think. It says for the 50 states, the year that the state joined the Union and the land area of the state. Okay, so our first variable is the year that it became a state, and then the second variable is the area, or basically how big the state is. Okay, so for my face-to-face classes, I like, you know, for the class to talk about it, and we talk a little bit about, you know, U.S. history. So what can you think? What were some of the first states? They were on the East Coast. They were the New England states. Okay, and I also like to pull up a map of the U.S. Okay, so let's, I don't know, let's look at this one. Maybe just zoom in. How's that? Okay. All right. So I like to ask them. Okay. So the first states were where? The first states were up here. Okay. They were along the East Coast because, you know, the Europeans were coming from the West, from Europe, and this is where they landed. Okay, couldn't really land anywhere else. So these initially they were colonies, okay, of Britain. So initially they were colonies, but then they were states. But notice here, guys, a lot of these states are some of our smallest states, are they not? You got Maryland, Delaware, New Jersey, Massachusetts, Rhode Island, or no, I'm sorry, this is Connecticut, Rhode Island, Massachusetts, Vermont, New Hampshire, okay? And then what happened? Well, we started pushing west, and that's been the history of our country. Then the states next, or the colonies next to these, or these territories, they were probably territories, they then became states, okay? And then it just kept going westward and westward and westward. So if you notice, there is a trend here. The smallest states are over here on the East Coast. These were the first states to become part of the Union. And then as we go west, as the years advanced, these states are larger in area. And then, of course, with the exception of Hawaii, Alaska was our last state, and it is the largest state by area. Okay, so there is a correlation there. As the years increased, okay, from the 1600s, well, I guess statehood started in the 1700s, but from the 1700s all the way until I think Hawaii was the last state, and I want to say 1954, but I'm not positive. So over, you know, roughly that 200-year time period, as the years advanced, the area of the states that were becoming part of the Union was growing as well, okay? So an increase in that first variable, it corresponds to an increase in that second variable. So that's an example of positive correlation. Okay, let me get back to Get back in my notes here. All right. So, as time advanced, okay, so too these subsequent states that were entering the Union, the land area, on average, okay, was larger and larger, okay, because the largest states are out west and the smallest states are out east. So we're going to go with a positive correlation here. Okay. Now, if you had had just as many large states on the East Coast as you did on the West Coast, then there might not have been any correlation there. All right, let's look at number 2, the last one here. Okay, so for cities, the latitude of the city and then the average high temperature in June of that city. Okay, so what are our variables? Well, the latitude, and it doesn't have to be cities, just think about latitude, the latitude of anywhere on Earth. Or let's just stick to the northern hemisphere, okay? The latitude, and the other variable is the high temperature in June, okay? So to think about this, let's get another map. Let's look at a world map. Should have already had these pulled up. Alright, let's maybe look at this one if we can. Zoom in again. Okay, so here we go. Here's a map of the world. Okay. So let's just focus on, well, we could also use the southern hemisphere, but let's just focus on the northern hemisphere. So this is the equator right here. Okay. So latitude is basically the position, how far away from the equator any place on Earth is, okay? So your positive latitude indicates a position in the northern hemisphere, and a negative latitude indicates a position in the southern hemisphere. So we're just going to stick to positive latitude. Now latitude is given in degrees. It goes from 0 all the way to the North Pole would be at 90 degrees. In fact, Little Rock is roughly 34 degrees latitude. So we're 34 degrees up from the equator to the North Pole, okay? So think about what would be happening here. So as we start increasing in latitude, what would the average temperature in June be? Well, think about what happens as you drive north, or as you go north in the northern hemisphere. Do temperatures typically become warmer, or do they typically become colder? They typically become colder. It doesn't really matter what month of the year it is. Okay, but in June, in Arkansas, June is hot, or it's starting to get hot. So if you wanted a break from the heat, you wouldn't go south. Or, well, you could go south, but you'd have to come down in here, to South America. But if you want to break in the heat, then you could head north. You could head up to some of the northern states or up into Canada, okay? So what I'm getting at is that as latitude increases, the temperature decreases. The average temperature in June would be decreasing, okay, because you're going north. And so an increase in latitude corresponds to a decrease in average temperature in June. So this is actually a negative correlation. Okay. All right, so we're going to say negative correlation. Okay. And just remember, guys, latitude is your first variable, and the average temperature in June, that would be your second variable. And similarly for number 1, your first variable would be the year, the actual year that the state became part of the United States or part of the Union. And then your second variable would be the actual area, land area of the state. And this would probably be in square miles. Okay. All right. So that is it for 5E. And for chapter 5 for that matter. Okay. The next video will be starting chapter 6 with 6a. We'll start looking at actually So let's say we've got out, we've gathered our data. Okay, now what do we do with it? Okay, we're going to find some statistics, and that's what section 6a is going to be about. Okay, so I'll see you there. So just remember, correlation does not mean causation. Just because two variables or two things are correlated or associated does not mean that one is causing those effects in that second variable. But we always want to assume that.